everyone, thank you so much for clicking onto the video. Today's first learning objective is to be able to plan reaction schemes of up to 4 steps to form both familiar and unfamiliar compounds, and then to understand methods of increasing the length of the carbon chain in a molecule by the use of magnesium to form Grignard reagents and the reactions of the latter with carbon dioxide and with carbonyl compounds in dry ether. So now we're going to look at carbon-carbon bond formation. Forming carbon-carbon bonds in a reaction is very important as we can synthesize new compounds containing more carbon atoms. And there are a few ways in which we can extend the carbon chain, and we're going to look at 4 of these reactions. So the first is when we form nitriles from haloalkanes, and then we're going to look at forming nitriles from carbonyl compounds, so aldehydes and ketones, so the compounds with this C double bond O group. And then we're going to look at Friedel-Crafts alkylation and acylation of aromatic compounds. So in particular, we're going to look at benzene. And these are both in the presence of an aluminium chloride catalyst. So the first reaction we're going to look at is forming nitriles from haloalkanes. And this is a nucleophilic substitution reaction, and where Cn- will act as a nucleophile, and this will substitute the halogen in the haloalkane. So the reagent we use is potassium cyanide in ethanol or sodium cyanide. And so the nucleophile acting is the Cn-. And so we're going to look at the reaction of 1-chloropropane and potassium cyanide. So I'm going to draw out 1-chloropropane. So we have CH3, CH2, and then a carbon with 2 hydrogens, and then a chlorine. And so because chlorine is much more electronegative, we have partial charges. So we get a partially positive charge on the carbon and a partially negative charge on the chlorine. And it's this partially positive carbon which attracts the nucleophile because it has a spare pair of electrons. So we have the nucleophile here, which is a Cn-, and we have a spare pair of electrons. And so these 2 electrons are attracted to this partially positive charge on the carbon, and so they attack it. And then what happens is that the electrons from this bond here between the carbon and the chlorine move towards this chlorine, and we get this nucleophilic substitution reaction. And so what we form, CH3, CH2, CH2, and then now we have a cyanide attached. And we also have the Cl- which has been substituted out. So the product we have is butane nitrile. And as you can see, we have 1 extra carbon. So in this nitrile, we have 4 carbons, whereas in the haloalkane, we only have 3. So we've extended the carbon chain by 1 by going through this nucleophilic substitution reaction. And so overall, what we have is CH3, CH2, CH2Cl, added with some potassium cyanide will form this butane nitrile. So CH3, CH2, CH2Cn, and then we'll have potassium chloride as the byproduct. So the second reaction we have is when we form nitriles from carbonyl compounds, and these are nucleophilic addition reactions. So again, this Cn- will act as a nucleophile, and it's added onto the delta positive carbon in this CO double bond, and a hydrogen is added onto the delta negative oxygen. And so what we form are hydroxynitriles. So nitriles where we also have an OH group. So the reagent we use is sodium cyanide or potassium cyanide mixed with some sulfuric acid, and the nucleophile is the Cn-. So we're going to look at the reaction of propanone and hydrogen cyanide. So hydrogen cyanide is actually too poisonous to use on its own, and that's why we have to mix either sodium cyanide or potassium cyanide in some sulfuric acid, because the sulfuric acid will provide that H+. And so what we have is, firstly, drawing out propanone, we have CH3, C double bond O, and then CH3. And so we have a delta positive charge on the carbon because oxygen is much more electronegative. So the oxygen will have the partial negative charge. And then we have our nucleophile, so this Cn- with the spare pair of electrons. And these electrons are really attracted to this partially positive carbon, and so they move towards this carbon and attack it. And then what happens is that the electrons from this bond then move towards this oxygen. So what we form is CH3, and then we've got a carbon and an oxygen, and now we have a spare pair of electrons on this oxygen. So this oxygen is now negatively charged. And then we also have the cyanide and a CH3 group now attached. And now we have a H plus from the acid, the sulfuric acid. So H plus attacks, and this is from the solvent. And this is attracted to the 2 electrons on this oxygen with a negative charge. And so what happens is that this H plus then attacks this oxygen, and then we can form our hydroxynitrile. So we have CH3 and then COH, CH3, and then the cyanide. And so again, we can see that we've added another carbon. So we started off with 3 carbons, and now we have 4. And the overall equation is this propanone, so CH3, COCH3, reacts with to form CH3, COH, CN, CH3. Now we're going to have a look at reagents used in organic chemistry. So firstly, we're going to look at oxidizing agents, and the oxidizing agent that we've looked at is potassium dichromate. So this is our K2Cr2O7, and this has to be acidified with a dilute sulfuric acid in order to oxidize alcohols. So what we can do with this potassium dichromate is oxidize primary alcohols to aldehydes and then eventually to carboxylic acids, or we can go straight from a primary alcohol to a carboxylic acid. And we also need to know that secondary alcohols are only oxidized to ketones. And then for reducing agents, we need to know that different reducing reagents have different capabilities. And that's why we've looked at 3 different reducing agents. So the first is sodium tetrahydride borate, or we can also call it sodium borotetrahydride. And actually an alternative to this NaBH4 is actually LiAlH4. So either of these can be used. And it can be used in aqueous solution. And these reducing agents will reduce polar unsaturated groups, such as C double bond O, because we have the carbon, which is a partially positive atom, and then we have the oxygen, which will be partially negative. And this is because the oxygen is much more electronegative than the carbon. However, these reducing agents won't be able to reduce non-polar bonds, so such as the carbon-carbon double bond. And this is because it generates the nucleophile H-, which can only attack this carbon with a partially positive charge, but it's repelled by the electron-rich carbon-carbon double bond because we know that the double bond is an area of high electron density. The second reducing agent we have is hydrogen with a nickel catalyst. And this is what we use to reduce carbon-carbon double bonds, but not carbon-oxygen double bonds. And this is actually also used to reduce nitriles. So to get from a nitrile to an amine, we could use hydrogen with a nickel catalyst. And then the third reducing agent we need to know about is tin and hydrochloric acid. So this is used to reduce an RNO2 group to an RNH2. So for example, we could have a nitrobenzene, and we would reduce this to a phenylamine. And then finally, we need to know about dehydrating agents. So alcohols can be converted to alkenes by passing their vapors over heated aluminium oxide or by acid-catalyzed elimination reactions. Now we're going to have a look at the alkylation of benzene. So this is one of the methods we can use to add more carbons onto aromatic compounds. So in the presence of an aluminium chloride catalyst, benzene will react with haloalkanes to form alkyl benzenes. So just benzenes with an alkyl group. And this is an example of an electrophilic substitution reaction. And the reagent we use is a haloalkane in the presence of an aluminium chloride catalyst, and the electrophile is the RCH2 plus group. So for example, looking at the ethylation of benzene, the haloalkane we're using is some kind of haloethane. So for example, if we used some chloroethane, what we would get would be the benzene reacting with some chloroethane. So we have CH3, CH2, Cl, and this will react in the presence of this aluminium chloride catalyst. And this will form benzene with this newly attached CH2, CH3, and what is removed is HCl, because we removed a hydrogen from the benzene, and this will react with the chloride that's been taken away, well substituted out of this chloroethane. And so what we've formed is ethyl benzene. So in this case, our electrophile is this CH3, CH2 plus ion. This is our electrophile. And as you can see, we've added some more carbons onto this aromatic compound. And the last reaction we have, which extends the carbon chain, is the acylation of benzene. So in the presence of an aluminium chloride catalyst again, benzene will react with an acyl chloride, so this is an acid derivative, to form an aromatic ketone, so a ketone with a benzene ring. And this is an example of an electrophilic substitution reaction again. And the reagent we use is an acyl chloride in the presence of an aluminium chloride catalyst, and the electrophile is this Rc double bond O plus ion. So for example, in the acylation of benzene to form phenol, so we start off with some benzene, and then we're going to react this with some propanoyl chloride. So that's just for this example. So we have CH3, CH2, and C double bond O Cl. And we know that we have to use propanoyl chloride because the product is phenylpropanone. And so in the presence of an aluminium chloride catalyst, what we form is the benzene ring, but this time we have a C double bond O, and then we have CH2, CH3, and this is our phenylpropanone. And we also form HCl. And this is because we've taken off a hydrogen off this benzene ring and reacted it with the chlorine from this propanoyl chloride. So again, we can see that we've extended the carbon chain. Now we're going to look at Grignard reagents. So we can also extend the carbon chain using these Grignard reagents. And Grignard's method of synthesizing organic compounds involved the use of organometallic compounds which contained some magnesium. And these are what we know now as Grignard reagents. And they're made by heating under reflux the chosen haloalkane with magnesium in a solvent of dry ether. And haloarenes such as bromobenzene can also be used. Bromoalkanes are preferable compared to other haloalkanes. And these Grignard reagents contain magnesium, which is covalently bonded to both the alkyl group and the halogen. And they also react with water, so they're both made and used in a solvent of dry ether. And a general equation we have for the formation of a Grignard reagent is firstly we have our haloalkane. So here we're going to use a bromoalkane. So we have the R group, which is the alkyl group, and then we have the bromine. And if we add some magnesium, what we form is the R group, and then we have the magnesium, and then we have the bromine. So the magnesium is covalently bonded to both this alkyl group here and also the bromine, which is the halogen. Start looking at these Grignard reactions. After a Grignard reagent has been made, it can then be converted into a range of organic compounds depending on the reagent used. And having made the appropriate Grignard reagent, the second reagent, which we're going to look at carbon dioxide or the carbonyl compound, is added. Then a dilute acid is added after to obtain the desired organic product. So firstly, we have the Grignard reagent, and then we add the second reagent, and then finally a dilute acid. And we're going to look at the reactions with carbon dioxide and also carbonyl compounds. So we're just going to look at some general equations first. So firstly, with the carbon dioxide, what we have is we have the Grignard reagent. So this is a bromoalkane added with a magnesium to form this Grignard reagent. And what we form when we add carbon dioxide is an R group and then the carboxylic acid. So what we form is a carboxylic acid. And then with methanol, what we form is we have, again, this Grignard reagent. And this time we form an R group and then we have CH2OH. So what we form is a primary alcohol. And then with an aldehyde, we again start off with this Grignard reagent, but this time we form a secondary alcohol. So we have an R group and then an R dash and then CHOH. So this is a secondary alcohol. So because we're using an R here for the Grignard reagent, that means that the aldehyde we actually denote with an R dash, which could be the same as this R group in the Grignard reagent or different. And then finally looking at the ketone, we start off with the same thing. So we have this Grignard reagent, but this time we form a tertiary alcohol. So we have an R group, another R group and another R group, and then we have COH. So this is a tertiary alcohol. And again, all of the R groups could be the same or they could be different. And also note that the two at the top, so the reactions with carbon dioxide and methanol, extend the carbon chain by 1. Because in the Grignard reagent, we don't have any carbons, and then we suddenly get a carbon here when we react it with carbon dioxide, and then the same thing with methanol. And then with the aldehyde and the ketone, it's variable depending on how many carbons we have in the R group. Now we're going to look at examples of Grignard reactions. So firstly, we're told to write equations for the formation of 3-methyl butanoic acid using Grignard reagents. So first let's draw out this molecule. So we have butanoic acid, so we have 4 carbons in the chain. And on the last carbon, well, on the first carbon, we should have the double bond O and the OH. And so we have 3-methyl. So if we label this carbon 1, then this one must be the third carbon. So we have a methyl group here, and then we have hydrogens everywhere else. And so first step is always to generate the Grignard reagent. So we have step 1. And because the COOH we've seen comes from reacting it with carbon dioxide, this means that we have to have the left-hand side of this molecule being from the haloalkane. So we have CH3, CH, CH3, and then CH2, and then we'll use a bromoalkane. And then we react this with magnesium, and now we can form our Grignard reagent. So we have CH3, CH, CH3, and then CH2. So this is our R group. And then we have magnesium, and then finally the bromine. And now we know that we have to react it with carbon dioxide to form this carboxylic acid. So step 2 is reacting this with reacting this Grignard reagent with the carbon dioxide. So we have CH3, CH, and then CH2, MgBr, and then we add carbon dioxide. And what we form is CH3, CH, CH3, and then CH2. So we still have this R group. And then we have COO and then MgBr. So instead of having the hydrogen of the carboxylic acid, we actually have this MgBr on the end instead. And so the last step is to add dilute acid to form our carboxylic acid. So we have step 3, CH3, CH, CH3, and then CH2, and then COO, MgBr. So we actually write this as adding some H2O, so we're adding dilute acid, and so we can form CH3, CH, CH3, CH2, COOH, and also MgOH, and then Br. So this is always what we go through. So in the second step, we always form MgBr at the end instead of what we actually want. And so the 3-methyl butanoic acid is formed in step 3. And then for the second example, we're going to write a reaction scheme for formation of 2-methyl propanol. So firstly, looking at the structure of this alcohol, we have propanol. So we have 3 carbons in the main chain. And the OH is on the second carbon because we have a 2 here. So we must have an OH on this middle carbon. And we also have 2-methyl, so we also have a CH3 group on this carbon. And then we have hydrogens everywhere else. And now we look at the central carbon, and because we have 1, 2, and 3 methyl groups, this is a tertiary alcohol. And we've seen that in order to produce a tertiary alcohol, we have to react the Grignard reagent with a ketone, CH3Br. So now I'm going to write it as a reaction scheme instead. So we can start off with some bromomethane. And if we add some magnesium with some ether, then what we can form is CH3, so the R group, and then magnesium, and then Br. And now we need another, and so we have to use propanone because it has to be a ketone. So we have CH3, COCH3. And then after that, we then need to add some dilute acid, so H2O with some H plus ions. And then what we can form is this 2-methyl propanol. So we have 3 CH3 groups on a carbon with an OH. So now we're going to look at organic synthesis. The synthesis of an organic compound can involve several steps, and these are factors that chemists aim for when planning synthetic routes. So synthetic routes are just routes that we can take to get from one organic compound to another. So for example, we could make an amine from an alkene. So the first factor we have to look at is using non-hazardous starting materials and processes that don't require solvents. And this is because solvents are often flammable and they're also toxic, and so we get some safety risks. And the second point is that if the solvent has to be disposed of after the reaction is complete, then we'll have a lot of waste which will be produced. The reason we want to use non-hazardous starter materials is that we want to limit the potential for accidents and environmental damage. The second factor we need to take into consideration are reactions that have a higher atom economy. And so chemists are also concerned with designing processes that aren't too wasteful. And if a reaction has a high atom economy, then we get less waste because more of the reactants will form the products. So processes with high atom economy and high percentage yields are preferred because they convert more of the starting material into useful products. And so we get less byproducts, and so we get less waste. And the last thing is that we want to have synthetic routes that have fewer steps. And this is because waste can also be reduced by designing synthesis routes that have as few steps as possible. And this makes sense because if you have a think about a really, really long synthesis that has lots and lots of steps, that means we get lots and lots of byproducts that we won't actually use and they won't be useful for us. So that will be waste compared to if we have a fewer steps, then we have fewer byproducts and so we have less waste. So now we're going to look at the relationships between functional groups. So this is basically a mind map of how to get between different functional groups. And you should probably have this memorized in your head because it'll make it a lot easier to think of reaction schemes. So I'm first going to start off with the alkane. And we're firstly going to produce a halogenolalkane or a haloalkane from this alkane. And there's only one reaction that will make a haloalkane from an alkane, and that's free radical substitution. And that's where we have a halogen and also UV light, and we can add the halogen to the alkane to form this haloalkane. And we can also reverse this, and so this is why this arrow goes two ways. And now looking at a halogenoalkane or a haloalkane to an alkene, this is our elimination reaction. Hot ethanolic OH minus to eliminate the bromine to form a double bond. And so that's how we get the alkene. So I'm actually going to put those in different colours. So for the free radical substitution, we need a halogen. And really important is that we need UV. And for this elimination, we need hot ethanolic sodium hydroxide. And then to get from a haloalkane to a nitrile, this is a nucleophilic substitution reaction. Because we're substituting the halogen with a CN. And so what we need is a CN minus ion. So how we get that is we add potassium cyanide followed by some acid. And then the next reaction is from this haloalkane to this amine. So this is again a nucleophilic substitution. And this is where we used ammonia as the nucleophile. And that was also our reagent. And now we're going to look at an alkene to an alcohol. So this reaction is a hydration reaction. And we have to add some water. And we would also need the presence of a strong H+ catalyst. So we would need an acid catalyst. And now we need to look at the haloalkane to an alcohol. So we missed that out before, but this is also a nucleophilic substitution reaction. But this time we're using an OH- as the nucleophile. And so the reagent we need is something like sodium hydroxide. But this time, instead of it being hot and ethanolic, like when we had the elimination reaction, we need it to be dissolved in water. So we need it to be aqueous and also cold. So we have cold, aqueous, sodium hydroxide or potassium hydroxide. And so what we can do to get from an amide to a nitrile is dehydrate it. So this could be our dehydration reaction. So this is if we have the arrow going this way. And this free radical substitution is actually just from an alkane to a haloalkane. And the elimination reaction is from the haloalkane to the alkene. And so we have a dehydration reaction to go from the amide to a nitrile. And what we need is we need some phosphorus oxide. So we need to heat it with phosphorus oxide. And then to go from a nitrile to an amine, this is a reduction reaction. So we have a reduction reaction here. And this is our reduction that we looked at with the hydrogen and nickel catalyst. And to get from a nitrile to a carboxylic acid, this is a hydrolysis reaction. So here we have hydrolysis. And we need some water and also a H plus catalyst. So we need water and some kind of acid. And then this reaction here to get from acid chloride or an acid anhydride to an amide. So all of these acid chloride and acid anhydride reactions are all acylation reactions because these are both acid derivatives. So here we have an acylation reaction. And the nucleophile we use to form an amide is ammonia. So that is our reagent. And we can actually call these acylation reactions nucleophilic addition elimination reactions as well. And it's the same thing. So we have nucleophilic addition elimination. And so this is also an acylation reaction. But this time our reagent is water. And then to form an ester, we also have an acylation reaction. But this time our reagent is a primary alcohol. And now we only have a few more, and these ones are the ones which are a bit more simple. So first I'm going to look at the alcohol, aldehyde, carboxylic acid, and ketone. So to get from an alcohol to a ketone, what we need to do is oxidize it. And we need to remember that only secondary alcohols will oxidize to ketones. And how we do that is using potassium dichromate and a H plus ion, so a H plus catalyst. So if we're going this way, then we have oxidation. And if we're going this way, we have reduction. And so for reduction, what we use is sodium borotetrahydride or LiAlH4. And for oxidation, what we use is potassium dichromate with a H plus catalyst. And this is the same for an alcohol to an aldehyde and a carboxylic acid. So primary alcohols will oxidize to an aldehyde and the aldehyde will oxidize to a carboxylic acid. So going this way, we have oxidation, and here we have oxidation as well. And these are both using potassium dichromate with a H plus catalyst. So if we go in the other direction, so from an aldehyde to an alcohol, we have the same thing. So we have a reduction reaction here. So we use sodium borohydride or lithium aluminium tetrahydride. And we have to remember that we can only oxidize an aldehyde to a carboxylic acid, and we can't go the other way. We can also go straight from a primary alcohol to a carboxylic acid. So this would be an oxidation reaction. And we would use the potassium dichromate with a H plus catalyst. And then to get from a carboxylic acid to an ester, this is an esterification reaction. If we went the other way, it would be a hydrolysis reaction. And for esterification, we need an alcohol. And for hydrolysis of an ester, we need a H plus catalyst and also some water. And then to get from an ester to an alcohol, again, this is an esterification reaction. If we go from right to left and from left to right, this is a hydrolysis reaction. And so again, with the esterification, this time we need an acid, so we need a carboxylic acid or an acid derivative. And then for hydrolysis, we need water and H plus catalyst. So now we're going to have a look at the relationships between aromatic compounds. So all the compounds which have a benzene ring. So let's start off with benzene. So we have benzene in the middle. And now we're going to think about all the different things that we can produce from benzene. So firstly, we can go through halogenation. So this is where we add a halogen in the presence of a halogen carrier. So we can either go through bromination or chlorination. So if we go through bromination, we'll form benzene with a bromine attached. And so this is bromobenzene. And then we can also go, and this will form chlorobenzene. So here we have bromination. And chlorination. And so we've reacted the benzene with some bromine with a halogen carrier, so it has to be a bromine carrier. So for example, we could have iron bromide. And then for the chlorination, we've added chlorine with the presence of a chlorine carrier, so some aluminium chloride, for example. And with benzene, we can also go through nitration, and this is where we add a nitro group. So what we form is a benzene ring, but this time we have a nitro group attached instead of one of the hydrogens. And so this is nitrobenzene. And this can then be reduced using some tin and hydrochloric acid to form an amine. So we can have phenylamine. So this has become benzene with an NH2 group. So this is phenylamine. And then with this phenylamine, we can then add some bromine. And so we'll form this benzene with this amine group, and then also 3 bromines. So this is 2, 4, 6 tribromo nitrobenzene. And so what we've done in the first step is reduced it. So this is reduction. And we've added some hydrochloric acid with a tin catalyst. And then for the second step, we've added some bromine. And then what we can also do with benzene is we can go through Friedel-Crafts, and we have either Friedel-Crafts alkylation or acylation. So firstly, looking at alkylation, what we do is basically adding an alkyl group to it. So we're adding a haloalkane, and so it's going to replace halogen from the haloalkane to form this alkyl benzene. So what we form is this benzene ring, and now we're going to have a methyl group attached to it. And so what we've done is gone through alkylation, or this is also called Friedel-Crafts alkylation to be more specific. And what we've done is added some chloromethane in the presence of aluminium chloride catalyst. And the final reaction we have with benzene is Friedel-Crafts acylation, and this is where we add an acyl group to this benzene. So we form something called an acyl substituted benzene. Or we could say an aromatic ketone. So what we form is benzene, and now we have a C double bond O attached and also a methyl group, or an R group depending on what we reacted with the benzene. And then this can also go through reduction, like reducing an aldehyde or ketone, so reducing the carbonyl group to form a benzene ring. And then this time we have the carbon, and then we have an OH, a hydrogen, and then a CH3. So this is an alcohol. And so what we formed in the alkylation is this methyl benzene. And then here we formed one phenyl. So the ketone takes priority, so it becomes the root of the name. And so this is one phenyl ethanone because we have two carbons. And what we form after reducing this would be one phenyl ethanol, because we reduced this ketone to an alcohol, which is a secondary alcohol. And so firstly, to get the one phenyl ethanone, what we've done is we've added an acid derivative. So in this case, we've actually added an acyl chloride. So we've added CH3, COCl, and we've also added some aluminium chloride catalyst, and this is an acylation reaction. And then here we've reduced it, so this is reduction, and this is using some sodium borohydride. So now we're going to look at how to work out a reaction scheme. So first of all, we start by writing down the formulas of the starting molecule and the target molecule. So we can see in the diagram that we have our starting material labelled A and our target material labelled X. And then the next step is to write down all the compounds which can be made from A. So these are B, C, D, and E, and all the ways in which X can be prepared. So we've got T, U, V, and W. And it's really important to keep the number of steps as small as possible, and this is to maximize the yield of the target. Sometimes you'll be able to see straight away that a particular reaction will be needed. So for example, if the target molecule has one more carbon atom than the starting material, then it's really likely that the reaction of cyanide ions with a haloalkane will be needed at some stage, as this is the only reaction we have where we can increase the length of the carbon chain by 1. So the example we're going to look at is the synthesis of propanoic acid from 1-bromopropane. So first, I'm just going to have a think about some reactions that I can have. So I'm going to start off with 1-bromopropane. So this is a primary haloalkane. So I'm just going to write that I have a primary haloalkane. And one of the reactions which comes to mind with primary haloalkanes, or haloalkanes in general, is nucleophilic substitution. And things that can act as nucleophiles are either negative ions or species that have that lone pair of electrons that can be donated to form a covalent bond. And so we can react primary haloalkanes with hydroxide ions, for example, to form an alcohol. So I can form a primary alcohol from this primary haloalkane, and this is by adding aqueous OH minus ions. The second thing I can do is also a nucleophilic substitution reaction. So this time I can add cyanide ions. So if I add some cyanide ions, then I get a nitrile, and I have a primary nitrile, because this Cn minus would replace the bromine. And then thirdly, I can also use ammonia as a nucleophile. So if I add ammonia, then I can form a primary amine. Because if you remember the nucleophilic substitution with ammonia, we have a second ammonia nucleophile that comes and attacks, and so we remove one of the hydrogens off the NH3 to form an amine, which is NH2. And then the final thing that we can do with haloalkanes is we can go through an elimination reaction where we have the OH minus this time heated and dissolved in ethanol. So we have alcoholic OH minus, and this would be to form an alkene, because we're basically adding a double bond and getting rid of the bromine. So these are the two reactions that can happen with haloalkanes. We can either get nucleophilic substitution, or we can get elimination. And so here we have our nucleophilic substitution. And this one is our elimination reaction. And now I'm going to do the same thing, but with the target molecule. So what we can make the target material out of. So this time I'll start with the material on the right. So we have the end thing that we want to get, which is our propanoic acid. So we have a primary carboxylic acid, and ways in which we can form this primary carboxylic acid is, firstly, we can undergo oxidation. So we can form it from either a primary alcohol or an aldehyde, because we know that primary alcohol will oxidize to an aldehyde, and an aldehyde will then oxidize to a primary carboxylic acid. So we have, we can get this from an aldehyde, and this would be using the potassium dichromate with a H plus catalyst, or we could also get this primary carboxylic acid straight from the primary alcohol. And so again, this would be using our potassium dichromate. We could also get this primary carboxylic acid from a nitrile. So we could have a primary nitrile, and we would achieve this by adding some water with a H plus catalyst. So that's a hydrolysis reaction. And we could also get a primary carboxylic acid by using an acid derivative. For example, we could have an acid anhydride or an acyl chloride. And the way we would convert an acid derivative to carboxylic acid would be adding some water. And we actually also use some H+ as a catalyst. So now we can label our reactions. So these first two are oxidation reactions. And then this third one is a hydrolysis reaction. And this last one is an acylation reaction. So the nucleophile we're using is water. And now we can start to see what our reaction mechanism would be. So this is what we end up with. And now what we do is we can cross off all the things which aren't the same. And so basically what we need to do is we need to find something that is in common with both of these intermediates. So we can see that we've got this primary alcohol here, and we've also got a primary alcohol here. So this could be a possible intermediate. Or we have a primary nitrile here and also a primary nitrile here. So this could also be an intermediate. And there's nothing else in common, and so all of these four can't be used. So we don't do these. And so we're left with either a primary haloalkane going to a primary alcohol going to a carboxylic acid, or a primary haloalkane going to a primary nitrile going to a primary carboxylic acid. So now we need to decide between the two of them. And how we do that is I'm just going to write out the different molecules, and we should begin to see why we can't use one of these. So we're going to start off with our primary haloalkane. So we have 1 bromopropane, which is CH3, CH2, CH2, Br. This is our 1 bromopropane. And so we've said that this can either form our primary alcohol or our primary nitrile. So our primary alcohol would be propanol, or propan-1-ol, sorry. And this is because we've used the OH- as our nucleophile. And so we would have aqueous NaOH as the reagent. And then the primary nitrile that we would produce would be CH3, CH2, CH2, and then Cn. So this is butane nitrile, because we have 4 carbons. And what we've done here is we've added some Cn-. So what we do is we add potassium cyanide followed by some H+. So now if we have a look at the other side, which is propanoic acid, which is our target molecule. So we have CH3, CH2, and then COOH. So this is propanoic acid. And we said that we could form this either from a primary nitrile or a primary alcohol. So the primary alcohol would be propan-1-ol. So we'd have CH3, CH2, and then CH2OH. So this would be our first one. And how we would produce propanoic acid from propan-1-ol. We actually need to label this one as well. Is that we would add potassium dichromate with a H+ catalyst because we're oxidizing it. So that would also be reflux. And the other way was using the primary nitrile. So we would have propane nitrile. So CH3, CH2, and then C triple bond N. And we could form this by a hydrolysis reaction, so adding water and a H+ catalyst. So this is our propane nitrile. So now we can eliminate one of these methods, and it's because here we have butane nitrile, but here we have propane nitrile, so they're not the same, and so we can't go through this method to get from 1-bromopropane to propanoic acid, and so we have to use propan-1-ol as the intermediate. So we've now found our reaction scheme. So what we have is that for step 1, we have 1-bromopropane, so CH3, CH2, CH2, Br, and this will form our CH3, CH2, CH2OH, which is our propan-1-ol. And this is 1-bromopropane. And what we've done there is we've added cold, aqueous sodium hydroxide. So we always write down the reagent and not the nucleophile. So we don't write OH minus, we write NaOH, which is the reagent. And then step 2 is propan-1-ol. So CH3, CH2, CH2OH. And this will go on to form our propanoic acid. So CH3, CH2, C double bond O, and then OH. So this is propanoic acid. And the way we do that is using oxidation. So we add potassium dichromate and a H+ catalyst, and this is a reflux.